Now we had started to deal with the real number system as it was the main building block of the n-dimensional space. And we actually have considered the algebraic and order structural properties of the real number system. We have observed that that does not suffice, those two kinds of structures. They do not suffice to determine what we know as the real number system. Then we went back to calculus and asked, well, if you are just to name one notion, what will be the central notion of calculus? And that was, the answer to that was the notion of limit. Now, what's the limit? Be it the limit of a sequence, be it the limit of a function as the variable approaches a given particular quantity. Now, what we say is, well, if a sequence converges to a real number, then the way to describe that is that the terms of the sequence get closer and closer, arbitrarily close, to what we refer as the limit of the sequence, or the same in the case of a function. The limit of a function, f of x, say, as x tends to a, well, that's a quantity to which the value of the function approaches arbitrarily, gets closer and closer to that value. Now, the title of this chapter, it referred to the topological properties, elementary topological properties of Euclidean spaces. Now, topology, in order to define a topological structure, we should be able to give a precise answer to the following question. Well, topology, the way we will consider topology, that's also referred to as point set topology. Given a point and a set, what it means for the point to be arbitrarily close to the set. Once we make this precise, that will determine the topological structure. So the question we are to deal with is, when is a point arbitrarily close to a given set? Okay, now, what is it which actually makes this, the answer to this question precise in calculus in the real number system? What property is that? Now, if you have a calculus book and if you wish to decide whether that's a good book or not, then one possible way is to check whether it starts with the so-called Supremum principle. What we will do is, as I said, we'll take the algebraic and order structural properties of the real number system as given to us. We will use all those properties freely without any proof. But what we'll do is, in addition to them, we will assume the Supremum principle, which will say that every non-empty subset of real numbers, which has an upper bound, also has a least upper bound, a Supremum. That we will assume. And Based on that single principle, everything else concerning the real numbers that will follow. But in order to make that assumption, to state the supremum principle, we need to give some definitions now. Now, we start with a non-empty subset of R. And we take a real number, R. Now we say that Y is an upper bound of S if every point in S is less than or equal to Y. And I will use this symbol just as an abbreviation for all. If for all X in S, we have X less than or equal to Y. Similarly, we will say that Y is a lower bound of S if, well, again, naturally, for all X in S, this time Y is less than or equal to X. Now, let's also, for the sake of completeness, make the definitions of a supremum, or equivalently least upper bound, and an infimum, or equivalently greatest lower bound of S. Now we say that Y is a supremum of S if, now for that to be the case, Y should be an upper bound of S, firstly, if Y is an upper bound of S, and, as I said, supremum is synonymous to least upper bound. If this upper bound is least among all upper bounds of S, that is, for any upper bound Y prime of S, one has that Y is less than or equal to Y prime. So no matter what other upper bound Y prime you take, well, this could be Y as well, then Y should be less than or equal to that. Now we say that Y is an infimum of S if Y is a lower bound, first of all. Moreover, it should be the greatest among all lower bounds. For any lower bound, Y prime of S, one has that Y is larger than or equal to Y prime. Now, let me also write supremum. Another way of referring to that is least upper bound and infimum, that's greatest lower bound. Now, before proceeding to the supremum principle, let's have some simple examples. Now let us take S to be the set of all positive real numbers. That's a non-empty subset of R. Does it have an upper bound? Well, no, that's clear, but if you are to prove that, take any Y in R. We should show that this Y cannot be an upper bound of this set. How can we do that? We can produce some member in the set cap S, which is larger than Y. Now, well, this Y could be negative as well. If I take the absolute value of Y plus 1, this will definitely be a positive real number. This will be in S, and this is larger than Y. So Y is not an upper bound. S has no upper bound. Well, if it has no upper bound, it cannot have a supremum either, because the supremum in particular must be an upper bound. Now, what about the lower bounds of S? Well, every non-positive real number, 0 or any negative real number, it's an upper bound of this clearly. Every positive real number is larger than or equal to 0 or any negative real number. Every non-positive real number is a lower bound of S. What about an infimum of S? Does it have an infimum? 0 is an infimum of this set. So it's, well, in fact, this comprises. So I can rewrite this as follows. The set of non-positive real numbers is equal to the set of lower bounds of S. So 0 is an infimum of S. Now, we will see if a set has a supremum, then that must be unique. If a set has an infimum, that must be unique as well. But since we have not shown that yet, although it's a simple fact, I prefer to refer to an infimum and a supremum. Once we show that in case it exists, it's unique, then we will start to refer to the supremum and the infimum. Okay? Now, if we take S prime, just a bit different than this time including 0. Now, does it have an upper bound? By the same token as in here, this has no upper bound. Well, again, the set of all non-positive real numbers is the set of all lower bounds of this set, and 0 is an infimum. The only difference is that this 0, which is an infimum, belongs to here, while it does not belong to the set in the first case. This actually, although very simple, will be an important differentiation, an important difference between S and S prime topologically. But that's yet to come. As for the second example, let us consider the set of all rational numbers, rational real numbers. Now we will denote the set of rationals by Q. This will be actually the set of all real numbers of the form A over B, such that A, B are in Z. This will stand for the set of all integers. And for this to be well defined, B should be different than 0. Now, before proceeding, here, why rational? This is actually what? This is rational. Well, these are all numbers, real numbers, which are rational. Well, we read that as rational. But in fact, while rationality in economics is an important notion, well, it means being consistent with logic. But the origin of the word rational is rational, because people think that, well, if you have some wholes and then you divide a whole into equal parts, finitely many, then you take some of them and leave out some others. That's understandable. But if that's not the case, the number pi, for example, or the number square root of 2, they're difficult to understand. They're difficult to make consistent with logic. So actually, the everyday meaning of the word rational and irrational, well, that comes from rational and irrational. And numbers which are not rational, they're called irrational. Irrational. Now, what's the most famous irrational number? Square root of 2 is used as a typical irrational number. Why is it irrational? Now let's go back to high school and let's see how you can show that square root of 2 is not rational. Well, showing square root of 2 is not rational, that boils down to that it cannot be written as the ratio of two integers such that the integer in the denominator is different than 0. Let's suppose that we can write it like that. Suppose square root of 2 is equal to A over B for some AB in Z with B different than 0. In fact, if that's the case, then we can, without loss of generality, assume that A and B are relatively prime. Otherwise, we can actually shorten this by deleting the same prime numbers in the representation of both an A. So without loss of generality, assume that A and B are relatively prime. that is the only positive integer which is a common divisor of a and b, that's 1. Okay, but if this is the case, I can square both sides, and I can get 2 equal to a square over b square. But what does that mean? That means 2b square is equal to a square. But if that's the case, 2 divides the integer on the left-hand side, so it must divide a square as well. And I will use for this symbol, 2 divides a square. But 2 is a prime number. If 2 divides a square, it divides a as well. If 2 does not divide a, then it cannot divide a square, okay? But if that's the case, then 4 divides a square, if 2 divides a. But if 4 divides a square, then 4 divides 2b square. If 4 divides 2b square, then 2 must divide b square, but that implies that 2 must divide b, and these two statements, they contradict that a and b were chosen relatively prime. So they have a common divisor, which is larger than 1. So that's the contradiction. So square root of 2 is an irrational number. Now, there's an important fact about rationals and irrationals in R. We will borrow that from calculus from before. And it is, in everyday terms, it can be said, it can be phrased like this: rationals are everywhere in R, and irrationals are everywhere in R as well. Now, to make that precise, I can record that as a fact which we will be using freely. If I take any two real numbers, say a less than b, then between a and b, there's at least one rational and one irrational number. In fact, you can deduce from that between a and b, there will be infinitely many rationals and infinitely many irrationals, because you can further partition that interval into smaller ones, into smaller and disjoint ones. Each one contains at least one rational and irrational. But let me first complete the statement here. There is some x which is rational with a less than x less than b, and there is some y which is irrational. This is just to denote the set difference, the set of all real numbers which are not rational, with a less than y less than b. Now, here we were supposed to give an example of upper bounds, lower bounds, least upper bounds, greatest lower bounds. But after this regression, let us define T to be the set of all rational numbers such that x is less than square root of 2. This clearly is a non-empty subset of reals? Well, 0, for example, is a rational number and is less than square root of 2. So T is a non-empty subset of R. Okay. Does it have an upper bound? Well, square root of 2 by definition, well, I can take it like this as well. The set does not change since square root of 2 itself, which is not rational, does not belong to this set. Square root of 2 is larger than or equal to x for any member x in T. Now, square root of 2 is an upper bound of T. Well, if this is an upper bound of T, then any larger real number is an upper bound as well. But is it a supremum? Well, let y in R be any upper bound of T. In order to show that square root of 2 is a supremum of this set, let's proceed by contradiction. Well, square root of 2 is an upper bound. If it's not a supremum of this set, by definition of a supremum, this can only happen that there's another upper bound of T, say y, which is less than square root of 2. Now, suppose y is less than square root of 2. This supposition now should lead to a contradiction. To what contradiction does it lead to? Well, here you have two real numbers. One is less than the other. Then there must be some rational number, according to the fact stated above, which lies in between. By the above fact, there is some x in Q with y less than x less than square root of 2. But what can you tell about the relationship between x and the set cap D in that case? X is rational, x is less than or equal to square root of 2, whence x is in T, but with y less than x. But that's a contradiction. X is in T, y is an upper bound of T, y is less than x. It's not an upper bound in that case, a contradiction. So this means for any upper bound, y of T, one has that square root of 2 is less than or equal to y. What about lower bounds and infima of T? Does it have a lower bound? Well, it has none, but this time it depends upon the fact if this is the real line, it's 0. If we had not known that rationals are everywhere, if it were possible that you have rationals all on this side and no rationals to the left of that, then we would be in trouble. But as we know that rationals are everywhere, well, suppose it has a lower bound y, but then take y minus 1 as well. There will be some rational in here, but this will be less than y, and that will be in contradiction, since this x will be in T as well. That will be in contradiction with y being a lower bound. So I will leave writing that in full as an exercise to you. T has no lower bound. Okay. Now we are ready to get back to the Supremum principle. Any questions so far? This is all simple, but there's also some focus that we should be careful about the details. We should be precise. Now, we assume the Supremum principle, which is every non-empty subset which has an upper bound also has a supremum. We assume this, and we'll see in the sequel, both throughout the first and second semesters, that it is this which determines the topological structure of the real number system. Okay. Now, of course, here we have the duality between upper bounds and lower bounds, suprema and infima. Well, what is the corresponding infimum principle then? Well, what we expect is that every non-empty subset of R, which has a lower bound, also has an infimum. But once we assume this, that will follow as a theorem. We will deduce that using the Supremum principle, and that will be our first theorem. Now here, two assumptions. This is important. Non-empty subset, which has an upper bound. Both should be satisfied. Now, although we have defined upper bounds and lower bounds for non-empty sets, we could have defined that for the empty set as well. If you consider the empty set, and if you consider the definition of upper and lower bounds, which I have erased, but you have that in mind, what's an upper bound of the empty set? Everything is an upper bound, because it says for all members of the set S, okay, for all members X of the set X, of the set S, X should be less than or equal to Y. But since the empty set has no members, for all X, for all members of the empty set, well, if you say all elephants are pink, or the members are all green trees, well, no matter what follows that will be a vacuously, but a true statement. So for all X in the empty set, X is less than or equal to Y, no matter what Y you take. Everything is an upper bound, everything is a lower bound. Is there a supremum of the empty set? Well, everything is an upper bound, so there is no least one among them. Likewise, everything is a lower bound. There is no greatest one among them. So that's why this is important. Non-empty and is an upper bound. Now, in order to show that the infimum principle, the corresponding infimum principle, is a theorem, we'll prove that. But first, in order to make the proof of that as neat as possible, let's have a lemma. Let S be a non-empty subset of R. And now let us introduce the set cap T, which consists of the negatives of the members of S. Set T equal to X in R such that minus X is in S. Let Y be in R. Now the first statement, Y is an upper bound of S if and only if minus Y is a lower bound of T. Similarly, Y is a lower bound of S if and only if minus Y is an upper bound of T. Now, these are both clear statements, but again, there are four statements here, since both are biconditionals, but let's just go through the proof of 1/4 for a good reason. I'll refer to that after we go through the proof. 1, assume that Y is an upper bound of S. Now, what does that mean by definition of an upper bound? So, for all X in S, X is less than or equal to Y. Okay? That's just spelling out in detail what it means that Y is an upper bound of S. Now we wish to show that minus Y is a lower bound of T. Well, then let's take any member in T. Assume that W is in T. But by definition of T, what does that mean? That minus W is in S. By definition of T, minus W is an S. But what was Y? Y was an upper bound of S. Well, this is a member of S, so minus W is less than or equal to Y. Thus, W is larger than or equal to minus Y. No. Yeah. But then, for all members W in T, W is larger than or equal to minus Y, which simply means that minus Y is a lower bound of S, of T. So, minus Y is a lower bound of T. Here, the infimum principle is derived from the supremum principle by the order structural rule, if A is less than or equal to B, minus B is less than or equal to minus A. So that's okay. The rest is similar. Now, here, this was an assumption, the Supremum principle. Now we have the theorem to which we can refer as the infimum principle. Every non-empty subset of R which has a lower bound also has an infimum. Now let's since this claim is about any non-empty subset of R which has a lower bound, let's take any such set. Let S be a non-empty subset of R and assume that it has a lower bound that S has a lower bound, say Y, where Y is in R. We will now show that this set has an infimum. But this lemma, or just the structure of the theorem itself, well, makes us think that we should work with the set cap T, which consists of the negatives of the members of S. So set T equal to X in S such that, T is X in R such that minus X is in S. By the lemma over there, what do we know about Y and this set T? Well, minus Y is an upper bound of the set. By the above lemma, minus Y is an upper bound of T. What else do we need to apply the Supremum principle to this set T? It should be non-empty, but if S is non-empty, this set is non-empty as well. Also, T is non-empty as S is non-empty. So the conjunction of this by the Supremum principle implies that the set T has a supremum. By the Supremum principle, T has a supremum, say W. Well, we're interested in showing that S has an infimum. Okay? Well, if this is a supremum of W, what do we know about this, by definition of a supremum, it's in particular an upper bound of T, and moreover, it's the least one among all upper bounds. Okay? So W is, in particular, an upper bound of T. What does this lemma say? Well, if this is an upper bound of T, then minus W, that will be a lower bound of S by the lemma above minus W is a lower bound of S. Well, what we expect is that this will turn out to be an infimum of S. But, well, it's a lower bound, fine, that we know. What else should we show in order to complete the proof? Well, that given any lower bound of S, that will be less than or equal to minus W. That's the definition of a greatest lower bound. So let W prime be any lower bound of S. We should show that this W prime is less than or equal to minus W, okay? But what do we know? Now let's translate again this to terms of T. Then, what do we know about minus W prime? Well, that will be, if this is a lower bound of S, minus W prime will be an upper bound of T by this. Minus W prime is an upper bound of T. But what do we know about W? It is a supremum of T. That means as W is a supremum of T, this means that W is less than or equal to minus W prime, because this is least upper bound, this is an upper bound, so we should have this. But now, so minus W is larger than or equal to W prime by multiplying both sides of this by minus 1. But that completes the proof, because W prime, minus W, that's a lower bound of S. Moreover, for any lower bound of S, we have that minus W is larger than or equal to W prime. It's both an lower bound and it's also larger than or equal to any lower bound of the set. So, minus W is an infimum of S, completing the proof. So here, the crucial thing is this rule, which actually involves a combination of the order structure and algebraic structure. If A is less than or equal to B, then minus B is less than or equal to minus A. So we have now the infimum principle as well. Now let's have a very simple proposition. Let us take again any non-empty subset S of R. S can have at most one supremum and at most one infimum, which is clear. Now, S has at most one supremum, respectively at most one infimum. So this means, in other words, it either has no supremum, which is possible. It might have no upper bound at all. If it has one, then that must be unique. Now let's do that for the supremum case. Assume that y prime in R are both suprema of S. Well, if we can show that y and y prime must be equal to each other, that will complete the proof. But what? Y is a supremum of S, and y prime, being a supremum of S, is also an upper bound. So let me write it like that. As we have that y is less than or equal to y prime. But let's interchange the roles of y and y prime. Now, as y prime is a supremum of S and y is an upper bound, we have also y prime less than or equal to y, so y equal to y prime. For the infimum, similar for infimum. Thus, if S has a supremum, then we can refer to that as sup S, because if we had not shown that it's unique, then sup S would stand for a set rather than just for a real number. And likewise, we can also talk about inf S. Well, in optimization problems, we are more accustomed to talk of maxima and minima rather than suprema and infima. Well, what's the relationship between those, and what's the definition of a maximum now? And y in R. Now we will say that y is the maximum of S if y is the supremum of S and belongs to the set S. That's the only difference. Now I cannot need to talk of a maximum now. Well, since suprema are unique, in case they exist, if y is supposed to be equal to the supremum of S, in addition to belonging to the set itself, the uniqueness will follow. We say that y is the maximum of S if y is equal to the supremum of S and Y is a member of S. Likewise, we say that Y is the minimum of S if Y is equal to infimum of S and Y is in S again. Thus, going back to the examples we had, well, in the second example, square root of 2, that was the supremum of S, but it's not the maximum, because square root of 2 was not a member of S, a member of T. We refer to that as T in the second example. In the first example, when we had the set of all positive real numbers, 0 was the infimum, but not the minimum. But in S prime, the set of all non-negative real numbers, well, 0 was the minimum, okay? Now here, that distinction is crucial, and, well, as we will see, the topological structure that has to do with the topological structure of the set S itself, but suppose S is the set of all achievable utility levels by an economic agent. Well, it might have a supremum, but if that does not belong to the set, well, then the agent in question will have no optimal action. Well, suppose each action yields to some utility, and the collection of all utility levels thus achievable, they form the set cap S. If it has a supremum but no maximum, well, then what we expect is, well, the agent can come close, arbitrarily, possibly, to the supremum, but never achieve that supremum. There will always be something better. But now, that actually also inspires the following simple proposition. Simple, but conceptually crucial. Let, again, S be a non-empty subset of R. Assume that Y in R is an upper bound. Respectively, we have the lower bound case as well. Lower bound of S. Well, now, can we introduce a meaningful yardstick a meaningful condition under which this upper bound Y will turn out to be the supremum, or this lower bound Y will turn out to be the infimum of the set S. Now, Y is the supremum of S if and only if. We will now introduce a condition which essentially will say that this Y is arbitrarily close to the set S. We have not formalized that yet, and it'll wait for some time to get formalized, but we can do it like this. Now, this is the real line. Y is an upper bound. So the set S lies to the left of that, if this is the direction of the real line. Now, if I take any positive real number epsilon and consider Y minus epsilon, then for this to be the supremum, y minus epsilon should not be an upper bound. Because if y minus epsilon, for some epsilon positive, is an upper bound of S as well, this will not be less than or equal to y minus epsilon. But that means here we should have some x in S in this interval. Now let me write that. If and only if for every positive real number epsilon, there is some x in S with y minus epsilon less than x. Now let's consider the same situation for lower bound. Well, y is the lower bound of S. That means S lies to this part. If I take any positive epsilon, but this time consider y plus epsilon, for this to be the greatest lower bound, well, that means y plus epsilon should not be a lower bound. But that's equivalent to saying that there is some x in S to the left of y plus epsilon. If everything lies to this side, well then y plus epsilon would be a lower bound of the set in question, and this would not be the greatest lower bound because there would be an even greater lower bound for the set. So this means now y equals the infimum of S. If and only for every epsilon positive, there is some x in S with, this time, y plus epsilon is larger than x. Although we have gone through that on the picture, it's useful, well, just either this or that, one of these two statements, to prove one of these two statements. Let's do that. Now, since this is a biconditional, let's do the supremum version. Now, the proof will consist of two parts, but let's start first assuming that y is equal to sup S, and then show that the right-hand condition must be satisfied. Assume that y is equal to the supremum of S. Well, to show that the right-hand condition is satisfied, let us take any epsilon positive and show that for that positive epsilon, this is satisfied. Let epsilon be greater than 0. It is actually this part we have gone through on the picture. Well, as y minus epsilon is less than y, which is the supremum of S, y minus epsilon cannot be an upper bound of S. Y minus epsilon is not an upper bound of S. Well, that simply means, so there is some x in S with y minus epsilon less than x. That takes care of this part. If this is the supremum, then the right-hand side holds. Conversely, assume that the right-hand side holds. That is, for any epsilon positive, there is some x with this. Now, we are supposed to show that y is the supremum. It is already given by hypothesis that y is an upper bound of S. That's the first condition in being the supremum. By hypothesis, y is an upper bound of S. Now, the second condition is if you take any upper bound y prime of S, then y should be less than or equal to y prime. Now, let's proceed by contradiction. Suppose there is some upper bound y prime of S, which is even smaller than y. Y prime less than y. Now, the assumption that the right-hand side holds in conjunction with that should lead to a contradiction. If that happens, then that'll complete the proof. But here, set epsilon equal to y minus y prime, which is positive. Well, since this holds for any epsilon positive, it also holds for this particular epsilon. So by hypothesis, there is some x in S with y minus epsilon less than x. But what's this y minus epsilon? This is equal to y minus y prime, but that's just y prime. But now x is in S, and y prime is less than x. That means y prime is not an upper bound, a contradiction, implying that y prime is not an upper bound of S, as S has a member which is larger than y prime, but that contradicts that y prime was an upper bound, a contradiction. Thus, for any upper bound y prime of S, one has that y is less than or equal to y prime, so y is the supremum of S. Now, the infimum version, that's similar. Now, getting back to here, well, no matter how small I take this epsilon, there is some x in here. So, well, this can be interpreted that this y, this upper bound, is arbitrarily close to the set S. Because if I take even smaller, there still is some point. So, well, no matter what distance I prescribe, there is a point x of the set S, which is closer than that prescribed distance to the point y. Now, that will be actually our point of departure in defining arbitrary closeness, but that'll wait for some time. So here, what we have done is we have introduced the Supremum principle, in addition to the algebraic and order structural properties of the real number system, and that completes the description of the real number system. Well, we will delay the notion of a point being arbitrarily close to a set a bit later because, well, the making precise, that process will be the same no matter whether we work in R or in Rn, in the larger space, or in a class of spaces which will be referred to as metric spaces. So we will do that in the most general case, and it will be valid for R as well. So we will not do that over and over again at each level of generalization. Okay, any questions so far? So this is just the real number system and the Supremum principle. Next,